At very small scales, matter exhibits bizarre behavior. The ability to engineer materials with nanometer precision has allowed researchers to exploit this behavior to produce materials with novel and often exotic structural, electronic, optical, and magnetic properties. Despite propelling far-reaching advancements in the energy and healthcare sectors, however, nanomaterials have yet to really take off in the aerospace industry, partly because of the high risk involved in investing in technologies that have not quite matured to the lofty standard required by this industry. This issue of MRS Bulletin reviews some of the more promising applications of nanomaterials in human space exploration, which contribute throughout a spacecraft's entire journey out of Earth's atmosphere and back. The journey into space necessarily begins with successful liftoff. Even in this preliminary stage, nanomaterials can already serve a useful purpose. Because of their high surface area, nanoparticle fuels are highly reactive and burn at fast rates, making them well-suited propellants for aerospace applications. Researchers must, however, balance this reactivity with careful handling and storage. Coating the particles prevents them from clustering together and losing their highly reactive surface area, but it also reduces the amount of active material in a given fuel, thus decreasing performance. Once in space, whether in orbit or more ambitiously bound for the Moon or Mars, aeronautical systems need reliable ways to produce, store, and transmit energy. Advances in nanoengineering have allowed scientists to develop increasingly efficient and long-lasting silicon-based solar cells. Moreover, research on carbon composites has led to the development of flexible solar cell designs. For example, the Rollout Solar Array, or ROSA system developed in 2014, features a bendable solar cell array capable of unrolling to deliver power supplies and retracting when performing more delicate maneuvers in space. With respect to energy storage, work on carbon nanotube-based supercapacitors and rechargeable lithium-sulfur batteries is expected to yield systems with dramatically improved energy density while reducing the footprint of the electronics they power. Similarly, memory storage devices based on the mechanical movement of nano-sized switches and levers, and high-performance sensors based on nanomaterials are expected to provide electronics that are immune to radiation and consume low levels of power. Of course, these power systems are only as effective as the astronauts who operate them. Technologies for life support therefore represent another area in which nanomaterials, particularly those based on carbon, can make a significant contribution. Scientists have shown that nanometer-sized holes can be punched into a single sheet of carbon, a material called graphene, to form a super-thin water filter. Additionally, these carbon sheets can be rolled into nanotubes and decorated with nitrogen-based molecules called amines to remove carbon dioxide from the surrounding environment, refreshing the astronauts' air supply. Nanomaterials also show great potential for use in biological and chemical sensing. The combination of various biological sensing elements on a single microchip could allow astronauts to carry a medical diagnostics lab in the palm of their hand. And fully functional electronic noses, or e-noses, built using carbon nanotubes could help monitor levels of toxic chemicals such as carbon monoxide and nitrogen oxides. This need to replenish existing supplies extends beyond life support. There is a similar need to repair, rather than replace, materials while on long space flights. In this vein, researchers have shown that carbon-reinforced parts critical to spaceflight can be repaired by harnessing microwave energy to heat ceramic and polymer-based materials containing multi-walled carbon nanotubes. Scientists envision using this technique to process materials excavated from planetary surfaces. This ability to repair spacecraft materials will be particularly crucial to ensuring protection from harmful radiation in space and from the intense heat generated when re-entering Earth's atmosphere. From liftoff to re-entry, nanomaterials can be utilized in numerous ways to improve the current state of human spaceflight. This issue of MRS Bulletin highlights several of these applications while carefully outlining the technical and financial challenges that remain before they're fully adopted by the global aerospace industry.